So let me start off by introducing our team. I'm Marichen Vermeulen, your presenter for today, and together with Liesel Sterrenbach and Grace Elliott, we make up the Natural Sciences publishing team at the Answer series. In the wings today, we also have Gretel Lampe and Adriette Esterhuizen manning the chat, and Bonita Morgan is sitting here with me for technical and mostly emotional support today. So let's get started with the content. So why is the scientific method important? Why is it being taught? Now, as natural sciences, and maybe many of you joining also life or physical sciences teachers, I think we know the value of asking questions about the world around us, trying to understand processes like disease, our existence as a species, our impact on the planet, solutions to the problems we face. So science is really central to our human nature. By teaching even just the most basic ideas about science, we introduce our learners to the understanding that science and life in general is a continuous revision in progress, which is basically just saying that it creates that lifelong learner mentality which we hear about so often. Through the teaching of this process, we start to cultivate a very specific way of thinking, that science is not about continuously being correct, but becoming comfortable with uncertainty and change. It cultivates curiosity about the subject that you're teaching, but also about the world around us, and it hones those critical thinking skills that are essential in life and in understanding and answering questions in exams. So, when must you start teaching the scientific method? And the best answer here is as soon as possible. Learners are introduced to the scientific method in grade 7 for the first time, and recently, after engaging with our natural sciences community on this particular topic, I became aware that the depth of teaching scientific investigations in grade 7 specifically varies greatly from province to province, from teacher to teacher, and I understand that. Some teachers want to only focus on basics, like being able to write a hypothesis or an aim and identifying variables in grade 7 because they feel the rest of it might be too high a grade for learners. And after looking at the CAPS document and the ATP documents, it's shocking that there really isn't any concrete guidance or specific requirements given as to exactly what about the scientific method needs to be taught in grade 7 compared to grade 8, compared to grade 9. And that is worrisome because it leaves us all up to our own devices and clearly contributes to the varied responses that I received from the natural sciences community. It also begs the question, can we really teach the scientific method effectively without including all the concepts like validity, reliability, a control setup? I mean, all of these concepts need to be taught at some point, but when do you start with that? Grade 7, what do you build up into grade 8 and grade 9? I've also looked at other textbooks, and what often happens is certain terms may be watered down. So instead of using the term reliability, we're using accuracy. Instead of the term validity, you see the term fairness being used, which are not scientific terms, and they're not accepted or accredited in exams, and it's a term that learners will have to unlearn when they get into the FET phase. So I think we do them a disservice by trying to softball that content and using terms that are, as I said, not accredited or scientific. However, the teachers that did respond and said that they actually teach all the senior phase grades, 7 to 9, and they tackle the whole scientific method in grade 7, the whole shebang, all the topics. I also understand that because you alleviate pressure in later grades as the curriculum continuously becomes fuller. But I do understand in a grade 7 context that there is difficulty in determining where do I stop, what do I give and what don't I tell them about. Another reason I would say we need to start actually as soon as possible is because there are many studies that have been done specifically regarding social media about how many times you actually need to see an advertisement before you click on the shop or buy now button. And in fact, it's at least 7 times. Now, you can imagine if learners are being exposed to something that they're not scrolling through voluntarily, this content is being foisted upon them, they need to memorize it, that they're actually going to have to see it, hear it, write it, experience it many more times than just 7 times before it becomes part of their long-term memory. And I think rote learning or memorization often gets a bad rap in educational circles these days. You often hear people say, but you mustn't learn like a parrot. I always told my learners that however you want to refer to it, learning like a parrot, memorization or rote learning, that is the basis of all learning. That is how learning starts. You need to hear something multiple times, see it multiple times, write it multiple times in order for it to get into your long-term memory. So starting early with the scientific method enables learners to master it because they're getting exposed to it more often. So we need to teach these skills continuously in an integrated way with the content that is being covered in class. When you're giving homework or end of chapter exercises, make sure that there's at least one scientific investigation on the content. So continuously exposing learners to these questions will breed a familiarity and a comfortability with them. Okay, and then how to teach the scientific method, which is really the bulk of today's presentation. The best way is to start with an easily relatable example, and we're going to use the example of baking a cake. And as you work through this method, you add in exercises to solidify key concepts and continuously test learners' understanding as you go. And obviously you start off with the easier stuff, like just asking a question, then stating the aim, and then you gear up to your more difficult concepts like variables, reliability, etc. Now, some of you might find this webinar sounding fairly familiar, and your feeling would be correct, because this is a webinar that we have reworked from 2022, where we focused mainly on FET learners, and we created resources geared for FET learners, and everyone at that point wanted the slides for the presentation, but we didn't provide it as a resource. So today we're very happy, and I hope you are too, to announce that the slideshow will be part of the resources that you will be receiving from this webinar, and it will be available in both English and Afrikaans. So what we've done is we've expanded the slideshow, we've streamlined the presentation, we've made it more teacher and learner friendly in the hopes that you would be able to use it as is in your classroom. And like I said, we've translated the whole thing as well. So the presentation contains the whole scientific method, all the steps involved. So even though you might not want to teach all of them in grade 7, we decided to include them all in a well thought out narrative that makes sense as we work through this experiment. And because you have the full presentation, you can then use your own discretion to decide whether you want to teach all of these concepts or leave out certain steps for certain grades. But the hope is that once we've worked through this presentation today, you will see how we have simplified these ideas in a narrative way. So it's kind of following the sequence, the story that we're unpacking, and you won't feel that these concepts are too difficult to teach your learners. So we're going to work through the slideshow resource for the rest of this presentation, and we also have some other resources that you can print out that will assist you in teaching the scientific method. I'll quickly just browse through them at the end. And then just a reminder for those of you joining a bit late, if you want access to these resources, please make sure that you stick around to get the link to that feedback form in order to provide us with your preferred email address. Or alternatively, you can opt to join the WhatsApp groups where these resources and links will also be shared. So let's take a closer look at this through the example of how to teach the scientific method by baking a cake. So the next 30 to 45 minutes, I'm going to chop and change between presenting this section as if I was speaking to a group of learners and speaking to you directly as teachers by giving comments and tips on how to best present this topic in a fun and interactive way. The scientific method does have a lot of theory to understand, so the best thing to do is to break it down into a series of steps and to use a simple thought experiment to familiarize learners with this process. Please note that this presentation, along with all the other resources we prepared for today, are shared under a Creative Commons Attribution, Non-Commercial, Non-Derivative 4.0 International License. Basically, this means that you cannot use this work in any way that generates profit, and that you're not allowed to take our name off of it. You always have to provide credit to the answer series. So you're allowed to print it out, you're allowed to give it to your learners, but what you're not allowed to do is to take our name off of it or to sell it in some way. So the great thing about the slideshow document is that we've done all the thinking for you. We have formulated it in a conversational way to make it more engaging, relatable, and to help you unpack the more difficult concepts step by step. So the first thing of any good investigation, the first step is to make an observation or to ask a question about life. So, it's your friend's birthday next week, and since this is your very best friend, you want to bake them a cake. So you go to your mom's recipe book and you locate Granny's famous sponge cake recipe, which is also obviously your own favorite cake recipe. And going through the recipe, you see that only 1 teaspoon of baking powder is added to the batter. And you remember Mom telling you something about the fact that baking powder gives a cake its height. So in the pantry, you find 2 different types of baking powder: no-name baking powder and best baking powder. But which one are you going to use to give you the biggest cake? So you find yourself asking a question. Which type of baking powder will cause a cake to rise higher? And the 2 options here are no-name and best brand baking powder. But before we start baking this cake, there are some things we need to consider. And that brings us to planning this investigation. That is the second step. We need to plan how we're going to perform this experiment. In other words, we need to ask ourselves some important questions. And this is where we pause to brainstorm. So as a teacher, you would pause and engage with your learners about what things they would need to think of to perform this experiment. You can assist them by giving maybe the first 2 or 3 options on the next few slides, and then help to stimulate their thinking of more planning questions. So here are some of the questions that are included in the planning phase. So thinking about, how many cakes am I going to have to bake? Am I baking just 1 cake, 2 cakes? Am I baking 3 cakes or more? What will be different each time I bake this cake? What are you actually looking for every time? So the idea is that with each of these questions, you're going to pause, you're engaging with your learner so that they can actually, it's not supposed to be just a rhetorical question, they can think for themselves. This is a thought experiment. You want some interaction. You want them to talk about possible answers to these questions because you want to get to an initial setup for this investigation. Planning always also involves asking when, how, what, and where. When will I be doing this experiment? The birthday is next week. Am I going to wait until the day before the birthday? How will I be taking measurements? What equipment, in other words, am I going to need? How will I record my results? Where will I do this experiment? Do I have access to a kitchen? And then very importantly, do I need to ask permission to use that kitchen? And then what apparatus will I need to perform this experiment? And the list goes on. These are not the only planning questions. There are just 8 of them as a jumping off point for you. And they shouldn't, as I said, be rhetorical questions because I would use them to get my learners thinking. Now, after this class discussion, you will most probably and hopefully have gotten down to the basics of your experimental setup, which should look something like this. You're basically going to bake at least 2 cakes, and each of them will have different baking powder added to the batter, and you're going to check which one will rise the highest. So this is the basic setup. It is not the final setup. There might still be some changes as we work through this scientific method, but after this planning discussion, you should at least have reached consensus up to this point. So the third step is to convert your experimental question into an aim. So first revisit the question. Which type of baking powder will cause a cake to rise higher? To write an aim, I always like to imagine someone coming up to me and asking me, "So Marichen, what do you want to do?" And naturally, your answer will start with, "I want to." And that is what an aim is. An aim always starts with the word to determine, to investigate, to compare. So what do you want to do? I want to determine which type of baking powder will cause a cake to rise higher. Now, an aim also has a second criterion, and that is that it has to contain 2 variables in it. a dependent variable, which is highlighted there, the rise higher, so the height of the cake, and an independent variable, which is the type of baking powder. Now, why on earth are these variables, and what does that word mean? So here we segue into the understanding of variables. So if we look at the word variable, it comes from the word vary, which means to be different, to fluctuate, to change. So therefore, a variable is something that changes or that can change. And there are three of them that we always consider in scientific investigations: the independent, the dependent, and constant variables. So let's take a look at each of these, starting with the independent variable. So ways in which to understand the independent variable. It starts with the letter I, because I, the investigator, controls it. I decide what it will be. So this variable has set or predetermined values. Why? Because I made it so. I, the investigator, chose it to be so. This will also be the thing that is different between my different setups. And another way to think about it is that it's the thing that always happens first. First, I add the baking powder, then I watch what happens to the height of my cake. First, I give someone a type of medication, then I measure or watch whether it cures a particular symptom. First, I give a plant a type of water or liquid, then I watch how its growth responds. So on a side note, it's important that we give learners more than one way to understand or remember a difficult concept like a variable, because this is the stuff they struggle with. And here you can see 4 different ways of thinking about an independent variable. You can also just understand the word independent. If you ask learners, what does independent mean? If I tell you you're very independent, ma'am, it means that I'm not dependent on my parents, I do things on my own. Exactly, right? An independent variable does not depend on other things. It is not affected by any other variable. Next, we have the dependent variable. So this variable will change because of what I have done, because of the independent variable. So this is what is being measured. And another way to think about it is that this is the thing that happens second. So first I add the baking powders, the different types, that's my independent variable. Then I observe or measure the height of the cake. So my height depends on the type of baking powder. So dependent variables depend on other variables. They are affected by them, and we want them to be affected by the independent variable. Lastly, we have constant variables, which can also be called fixed variables or controlled variables. These variables can affect the results of our investigation in ways that we don't want them to. So we have to control them, fix them, keep them constant so that they don't interfere. So other ways of thinking about it is fixed, making it the same, controlled, keeping control over it, constant, making sure it stays the same. So we keep these variables the same so that their effects on the dependent variable, on what we are measuring, is not measured. And we'll elaborate on this in 1 or 2 slides. So in summary, getting back to the cake baking experiment, if we look at our aim, we said an aim has to contain 2 variables. So to determine which type of baking powder will cause a cake to rise higher, if you ask yourself, what is it that we're measuring in this aim? It helps identify the dependent variable, which is the height of the cake. For the independent variable, ask yourself, what does that depend on? What does the height of the cake depend on? It depends on the type of baking powder that I add to the batter. And then lastly, constant variables, we ask ourselves, what other factors besides baking powder could also influence the height of a cake? So let's unpack that concept. So here again would be a good place to brainstorm a bit with learners. Ask them to think of a list of things that could also potentially affect the height of the cake besides the type of baking powder. So have a class discussion. Ask them to think about things that are related to the recipe. We've added here a little link. If you want to look back at the recipe, you click on that and you can tell them, right, so if we look at the recipe, what other things besides baking powder is being added? And what about the eggs, the sugar, the hot water? Do you think that would also maybe have to be kept constant? What about the method? Are there any things here that we have to make sure we do the same every time? And then you can jump back to the slide that you left off of. So again, pause, have a brainstorm with learners, and then on the next slide or few, we have the actual answers to these questions. So if we look at the ingredients and we start from the top, we have the eggs. What about the eggs? Has to be the same. It needs to be the same sized eggs, the same brand of eggs. The eggs must be the same age, and maybe have a discussion with learners about these things. You know, why can't I use an ostrich egg in the one batter and a goose egg in the other batter? Okay, because the volume of these eggs are different, they have different properties, so obviously that then would affect the height of the cake. So learners would have to understand that these things need to be kept the same because they might affect the height of the cake, and then it's another variable besides baking powder that we are actually measuring. Then other ingredients, the flour, we have to use the same amount of flour, the same brand of flour, the same amount of sugar, the same brand of sugar, the same volume and temperature of water, the same volume and brand of vanilla essence, and the same amount and brand of butter. So you might not get through all of these, you might give them the first three and have them think about the rest. But then besides these ingredients, there are other factors that we also need to consider. So what else could affect how each cake bakes? And again, pause, have your class discussion about external factors in terms of the method and the materials. What about that needs to potentially be kept constant? So some of the things learners might come up with is the oven that you're using. It should obviously be the same oven and it must be set at the same temperature. And at this point, you're going to get a lot of kids telling you about the difference between granny's oven and mom's oven and which one burnt their cake. The same sized cake pan, asking them, but why can't I use a 20 centimeter and a 10 centimeter cake pan and then compare the height? Because obviously the batter is going to spread more in the 20 centimeter cake pan and there's going to be less batter into the height. Things like that. The time, baking time must be the same. The cakes must be placed in the oven at the same time. And then in terms of measuring, even though our independent variable is the type of baking powder, a constant variable should be the amount of baking powder. We have to add 5 milliliters or 1 milliliters or 1 teaspoon or whatever it is of both types. We can't compare two batters where we've added 15 milligrams of best brand baking powder but only 1 milligram of no-name baking powder. So we need to ensure that it is a valid test. Okay, but why? Why are any of these factors important? And that brings us into introducing the concept of validity. So let's see how to do that. Sure, that is a lot of stuff to try and control. Why can't I just bake two cakes with different types of baking powder and different numbers of eggs? I mean, surely this will still be there will still be a difference in the height of each cake. Well, of course there will. But then what caused the difference in height? Was it the eggs or was it the baking powder? Well, I don't know. It could be either. Exactly. And that happens because the investigation will then not be valid. You're allowing too many variables to affect the investigation at the same time, so you don't know which one caused the dependent variable to change. Oops. So there you can see a very good way of introducing the concept of validity, understanding the type of questions that a learner would normally have, but why can't I just add eggs and different baking powder? Because both of them affect the height, so which one was the one that affected the height the most, you know? So by keeping unwanted variables constant, you ensure the validity of an investigation. Your investigation is valid when it tests what it aimed to test. So the aim was to determine which type of baking powder causes a cake to rise higher, not to determine which type of baking powder and different numbers of egg caused the cake to rise higher. So if we want to investigate the effect of baking powder, we have to ensure that other variables other external factors do not also contribute to a difference in height of the cakes. A nice way to remember this is the V in validity is related to variables that need to be kept constant. Okay, so this would be a good place to stop your first lesson or start your next lesson with test your understanding, because that's a lot of stuff to remember. So we need to have a consolidation in between. So either at the end of the first lesson, you're going to consolidate, or at the start of the next lesson, you're going to use this exercise to just run through what you've done, make sure learners have got those concepts down. So you start off with an example that is not too far removed from the one used to introduce this topic. So instead of baking 2 cakes, we now have cupcakes that are baking in the oven. And instead of using different types of baking powder, we can see that we have changed the volume or the amount of baking powder added to each cupcake. So before you get to questions that are going to pop up here on the side, first you're going to pause on this and ask learners to dissect what is happening here, right? What do you see? What is happening? Okay, we see cupcakes. We see them being in the oven over time. So this is where they started out. That's where they ended up. And we can see different amounts of baking powder added to each cupcake. Now we're focusing the theory by asking specific questions. Right, so what is different between the cupcake setups? The amount of baking powder that was added. Okay, what do we call that variable, the one that is different between the setups? We call that the independent variable, because I, the investigator, make it so. I determine it. It's independent of other variables. What is it we are measuring in this investigation? The height of the cupcakes. What do we call that variable? The variable that we are measuring, what do we call that? The dependent variable. So this first example that you're doing is not too far removed from the example you used in the content to teach the theory, and then you gear up to a more difficult / unfamiliar example. So here again, we have a completely different experimental design. And first, you're going to stop and tell learners, right, what is happening here? Tell me what you see. Okay, we see 3 plants. We see a ruler next to each one. Okay, what do you think is the purpose of the ruler, right? We're going to measure the height of the plant. We see a soda can, a lemon juice or orange juice, and a water bottle. What do you think are the purposes of these different liquids? Okay, ma'am, we're going to probably water each plant with these different liquids. So have a discussion about the setup on the slide, help them understand what the experiment is actually about, what it is that we are investigating. We're looking at how different liquids would affect the height that a plant grows. Then we focus our knowledge by asking specific questions. So what is different between the plant setups? The type of liquid. What do we call that variable? The variable that is different, we call that the independent variable. What is it we are measuring? We are measuring how high each plant grows. What do we call that variable? The variable that we are measuring, we call that the dependent variable. What other factors must be kept the same? So here we test constant or controlled or fixed variables, and think about some examples here. Few of them that we've added on the slide is the same type of plant has to be used. We obviously have to give the same volume of each type of liquid. The person taking the measurements has to be the same. The plants should preferably be the same age. They should be planted in the same sized pots. We should observe them over the same time frame, etc., etc. You can say about the soil that needs to be the same species of plant. There are other options that you can add to this as well. What do we call these factors that should stay the same? We call them constant variables or fixed variables or controlled variables. And then lastly, why should these variables be kept constant, fixed, or the same? Because we want to ensure the validity of our investigation. Okay, so let's get back to the cake. In our second lesson, we're going to build up to the more difficult concepts. Okay, so we'll start off by first looking back at the previous lesson. What is it that we have done so far? So we have asked a scientific question. We have stated an aim for this investigation. We have identified the important variables, a dependent independent and control or constant variables or fixed variables. And we're going to basically see that the basic setup of the investigation is we have two setups, one that's going to have best baking powder and the other one no-name baking powder, and all the other factors, the methods, materials, and ingredients will be kept the same so that it is a valid investigation. Okay, then we're going to write a hypothesis. That is the next step. Okay, so what requirements must a hypothesis meet? And there are 4 of them. Firstly, a hypothesis must contain both the independent and dependent variables, same as the aim. It must provide us with a possible prediction or explanation of the relationship between the 2 variables. So we have to predict in some way how the brand of baking powder will influence the height of the cake. It must be a statement, which means that we can't start off a hypothesis with the words how, what, or which, because these are questioning words. So those would make it a question and not a hypothesis, which needs to be a statement. And then lastly, it must be testable. So let's look at some examples of hypotheses, because there is more than one way to write a hypothesis. A hypothesis can be stated positively. Best baking powder will cause the cake to rise higher than no-name baking powder. A hypothesis can be stated negatively. Best baking powder will not cause the cake to rise higher than no-name baking powder. Both of these are hypotheses. They might not be scientifically perfectly formulated, but nonetheless, they are hypotheses. However, it is always best to state a more general hypothesis if you can, where you remember that the criterion for hypothesis is that there needs to be a relationship between the 2 variables. So how do we expect the baking powder to affect the height of the cake? So an example of a more general hypothesis would be that the type of baking powder will or will not affect the height of a cake, or different types of baking powder will or will not affect the height of a cake. And again, in each of these statements, you have to have both the independent variable and the dependent variable that are highlighted there in different colors. It has to be a statement, it has to provide a general relationship, and it must be testable. Those are all the criteria for a hypothesis. Now, it's important to note that as long as these 4 requirements are met, the statement can be considered a hypothesis. And this opens up a lot of variations of the same idea and makes it sometimes a bit difficult to examine. You may have found that learners never seem to write the hypothesis exactly as it is in your memo, and that's bound to happen because of the fact that there are so many ways to do that. So what we need to do is we need to ensure that either our memos reflect as many possible options of the hypothesis as it can, or alternatively, we need to judge each hypothesis by the 4 criteria that make up a good hypothesis. Okay, so now we can finally perform the investigation and collect the results. So we bake our 2 cakes with different types of baking powder, and we keep the constant variables the same so that they don't affect our results. We measure the height of each of the cake, and then we organize our results into either a graph or a table, sometimes both. It really depends on the type of data that you are given that best represents it. And the representation of data is a completely different lesson in and of itself. It's very important that learners start to learn when to use graphs, what type of graphs fit what type of data. This is not something we address in this particular presentation. Sometimes it's just better to have a more visual representation of the data. So here it is in a table and a graph. And from this, we can now formulate a conclusion. So that's the next step. When we make a conclusion, it's important to look for a relationship between the variables, to study the results, to find that relationship. You need to make sense of the data. You should not just be quoting the data. That is not a conclusion. And I think this is one of the big differences in maybe how we approach this in senior phase compared to FET. So it's very important that from the senior phase, we start to teach learners that drawing a conclusion is not merely quoting or stating the results. It's looking back at your aim, looking back at your hypothesis, and then basically making sense of your results. So just a pop-up there that says, be careful of quoting the results. In other words, repeating what you see in a table or a graph. So an incorrect conclusion would be something like, no name baking powder caused the cake to rise to 15 centimeters and best baking powder caused the cake to rise to 20 centimeters. That is not a conclusion. That is just reading off the results. You have to make sense of that data by actually just continuing that sentence and maybe saying, therefore, we can conclude that. That is a conclusion. So let's draw a conclusion. We start by looking back at our aim. To determine which type of baking powder will cause a cake to rise higher. Then we look at our hypothesis. One of the many, I chose the different types of baking powder will affect the height a cake rises. And if we look at those two things, the conclusion that we draw is that best baking powder caused the cake to rise higher than no-name baking powder. I'm not quoting the centimeter values. If you chose to do that, you have to extend that sentence by saying, therefore, best baking powder caused the cake to rise higher, because that is the conclusion related to your aim. I know it's a silly example, but if a learner just said that no-name baking powder caused the cake to rise to 15 centimeters and best baking powder to 20, let's say I'm very stupid and I don't know that 20 is more than 15, it tells me that the learner might also not know that 20 is more than 15. So the conclusion is that best baking powder caused a higher cake. And that tells me that a learner knows 20 is more than 15. This is a silly example. Maybe when we look at other examples a bit later on, it becomes more clear. But just so we understand, the conclusion is not merely restating results. Okay, but now we still have the concepts of reliability and the control setup that need to be discussed. So let's see how we get into those. Great, says the A man. But how sure are you that best baking powder is always going to win? Well, it did this time. But if I were to repeat your investigation, how sure are you that I would get the same results? Not very sure. Then your investigation is not very reliable. Reliability refers to whether the results of an investigation are trustworthy and consistent. And it's very important that we actually relate this to real-world examples. I like to ask my learners, like, if we think about newspapers or magazines, what do you think is a reliable source? And then they might say something like Die Burger, and magazines like, jy moet nie altyd 'n huisgenoot artikel glo nie, the U articles or whatever. And you ask them, why don't you feel it's reliable? Just to unpack what that concept means in everyday life. And it's really about that a brand or a particular newspaper or whatever is trustworthy and its information is consistent. And that's why it's a reliable resource. So how do I make my investigation more reliable? Well, you can repeat your investigation many times. You can calculate an average. You can take a random sample if this is applicable to your setup. And you can increase the sample size. Okay? But why? Why does any of this help with reliability? So if you repeat an investigation and every time you do, you get the same or similar results, then we know that it's a tick for consistency. So that consistency is equivalent to reliability. If you repeat an investigation, you also get a lot of data. And with a lot of data, you can then calculate an average, which also improves reliability because it makes the data more generalizable to a larger group or phenomena. Taking a random sample is not applicable to this cake baking scenario. But let's say the investigation was an investigation into intelligence or IQ between boys and girls. If I was the investigator in that instance and I chose a random sample of boys and girls to participate, it means that I'm removing my investigator or experimenter bias. I am not specifically choosing intelligent girls to be part of my study because I want that to be the result of my investigation. That would skew my data because it produces a result that I intended to produce, and it's not then very representative or generalizable to a larger population of girls and boys. So in another experiment, taking a random sample would be a way of ensuring trustworthiness and consistency, which is equivalent to reliability. Then increasing the sample size also provides me with a larger data set from which I can calculate averages, and therefore it's more generalizable, more relatable to a larger population or phenomena. So an easy way to remember this is the requirements for reliability is to repeat the investigation, raise the sample size, take more readings and random sampling. And it's just really fun to do the thing the whole time. Okay, lastly, the control setup, right? We've covered all the difficult concepts now except for this one, and we've left it to last because I think it's the one that most teachers, especially in grade 7, might decide to skip over. But let's see how you could potentially introduce this. Okay, so let me get this straight. If I bake more cakes many times, my investigation will be more reliable. Yes. Okay, but there's one more problem. What is it? How sure are you that only baking powder affected the height of the cake? Well, what do you mean? I thought I kept everything else constant. Yes, but how much of the cake's height was only caused by baking powder and not by the eggs or the flour or the sugar? Sure, well, I don't know. That's why we use a control setup, because the control setup provides us with a comparison for our experiment and the results that we receive there. It's basically going to confirm that the independent variable caused what we observed, namely the dependent variable. So in the control setup, what we do is we remove the independent variable so that we can actually observe, measure, and compare its effects. So a way to remember this is the C for control setup is a comparison that confirms the independent variable caused the results. And what this means for our cake baking experiment is that technically every time we do this investigation, we should actually be baking 3 cakes. One cake that has no name baking powder added, one that has best baking powder added, and a third cake that receives no baking powder. Because the first 2 are our experimental setups, and the last one acts as the control so that we can actually see how much of the height was caused by the baking powder, whichever brand it was, alone. So remember that the control setup will have all the same ingredients, but no baking powder, because we actually want to see the effect of the baking powder alone on the height of the cake. And that's it. That is all the important concepts that we need to consider when performing scientific investigations. Now, this is obviously where you would stop and you need to consolidate this once again. So we've added an extension to the consolidation exercises that we added previously to the webinar. So let's see what we have here. So again, we go back first to the familiar examples, right? We have the cupcakes here once again, and now we're going to build on this example by adding an aim. So we've provided the aim for them to determine the optimum amount of baking powder for cupcakes to rise. Okay, so the first question is, what is a hypothesis for this investigation? Now, when you're given an aim, you say hallelujah, because the variables are provided, and it's very easy to then either go back to the question that you started with or forwards to the hypothesis. So here are some examples of hypotheses. 15 milliliters or 10 milliliters or 5 milliliters, whichever one you chose, is a baking powder is the optimum amount for cupcakes to rise, or a higher amount of baking powder, more baking powder is more optimal for cupcakes to rise, or a lower amount of baking powder, less baking powder is more optimal for cupcakes to rise. Remember that a hypothesis has to be a statement, must be testable, and it must contain the 2 variables in this scenario, which is the amount of baking powder, more or less, and the height of the cupcakes, and then stating a possible relationship between those 2 variables. That is the 4 criteria. Then you test their understanding by asking, right, so in this setup, where is the control? And the answer here would be the cupcake that has no baking powder. Now, this is a very nice visual because it actually helps to show exactly why a control setup is important. Because even when no baking powder was added to the batter, you can see that the cupcake still rose somewhat. So this clearly illustrates how a control is important. If we assume that all the variables were kept constant, all the others that we discussed, this would mean that some of that rising height of the cupcake occurs as a result of the other ingredients. And anything above this height, then therefore, can be attributed to the baking powder. So technically, what we would do is we would have to measure this one that had no baking powder added and then subtract that from the height of the other cupcakes to determine, what amount of this height was caused by the baking powder that was added. So this clearly illustrates the essence of a control setup. Okay, then it asks to state a conclusion for the investigation, and in order to do that, we first look at the results that we've seen. So if we look at the final picture here, even though we have no values added, what we can see is that the 5 milliliter cupcake rose somewhat, but seemed to collapse. 10 milliliter cupcake did the most rising. 15 milliliters baking powder seemed to collapse as well, and then no baking powder, there was some rising. Now, we're not going to just state those things, or if we had values, we can't just reiterate the results. We have to look back at the aim to determine the optimum amount of baking powder for cupcakes to rise. So conclusion here, because the aim asked for optimum amount, that is clearly the 10 milliliter baking powder. So we phrase the conclusion by referring to our aim. 10 milliliters of baking powder is the optimum amount of baking powder, and then add. Why? Because it caused the cupcakes to rise the highest. So it shows me that you could understand and interpret the results that were provided. The relationship here says optimum amount equals greatest rising of the cupcake. Then we look again at the second example that we did, and we build on that one. Okay, so again, we are given an aim in blue to determine which type of liquid will cause the most plant growth. So again, we're thankful for the aim because it gives us a lot of information to work with. And now it says, based on this aim, state the independent and dependent variable. So the independent variable from out of the aim is the type of liquid. And the dependent variable, now very important, when we look at the wording of variables, and if we are given an aim, we need to use the wording as it appears in the aim. So the aim here says plant growth. That is the dependent variable. What is being shown with the ruler is how plant growth was measured. That is a different question. The question how the dependent variable is measured is with the use of a ruler to determine the height in centimeters. So this is a very, very important thing to remember, and I'm going to give you two more examples to bring this home. Okay? When we are given an aim and we have to provide the dependent and independent variable, we get the phrasing of those variables from out of the aim. Plant growth is the phrasing for the dependent variable, but it is a qualitative phrasing. How do we quantify plant growth? We measure height in centimeters or millimeters or whatever, and that is what we record in the table. So what often happens with exams, and now I'm thinking ahead again to FET, right? Because we're using what's happening there, we're modeling that into what we want to teach in senior phase. So what often happens is learners are given an aim and they're given a table or a graph with the results. And the dependent variable's phrasing in the aim is different to what appears in the graph or the table. And we tend to teach learners, if you need the variable and they give you a graph, just go read it off of the axes. And we shouldn't be doing that because the dependent variable's wording and how it is measured could be two different things. Let's look at an example of what I mean here. So let's say you had an investigation about intelligence, as I've mentioned before, right? To determine, this is the aim that you're given, whether boys or girls have a higher intelligence. From this aim, we can take out the independent variable, which is the gender, boy or girl, and we can determine the dependent variable. As it is stated in the aim, is just the word intelligence, right? So IQ or intelligence. But intelligence, again, needs to be determined in some quantitative way. So what might happen after in this question that might be given, there might be a table with results that lists an IQ score. And the IQ score is how the dependent variable was measured, but it is not the dependent variable. The dependent variable is intelligence. Let's look at another example. To determine which age group of men is most fertile. Okay, that's what I'm setting out to achieve. So from this aim, the independent variable is the age group of the men. That's what I determine. What I'm measuring is fertility. But fertility is a qualitative term, and I need to quantify it in some way. I need to be able to measure it in some way to say this group is most fertile. So what might happen in a question like this is you would get a table or a graph where the sperm count of the group of men is provided. So again, in an exam, the correct answer in this case would be that it is the fertility of the men. That is what the dependent variable is. How the dependent variable was measured is the sperm count. Now, in the cake baking experiment or scenario, luckily both of them are the same. The aim is to determine which cake rises higher, and what you would see in the results in your table or graph is the height of the cake. So in that instance, great, learners can just look at the graph and it would be the same as what is in the aim. But sometimes in scientific investigations, what is stated in the aim for the dependent variable is more qualitative in nature, but it is measured in some quantifiable way. And we need to make sure learners understand that distinction. This is another reason why it's very important that when we write conclusions, we are not merely restating the results. We need to make sense of them. So if this was a question, then we would have to say, right, so if the sperm count of men in the group of 20 to 30 was the highest, we would need to make sense of that by saying, okay, that means they're the most fertile group. So that's a conclusion. A conclusion would not just be the sperm count of men in that group. Okay, now we've got that out of the way. So the next question in the slideshow is, write a suitable hypothesis for this investigation. So we're using the aim to do this. And again, there's more than one way to write a hypothesis. So options provided based on the aim. The most plant growth will be caused by the soda or the juice or the water, whichever you determine, or the type of liquid will affect the plant growth. One of these hypotheses, the top one, is a little bit more specific. The other one is more general, just stating that the liquid will affect the plant growth. And then in this experiment, which one is the control setup? And the answer is the plant that receives only water. Now, here is an ideal opportunity where learners might actually put up a hand and say, but ma'am, isn't the control setup where the independent variable has been removed? So in other words, shouldn't there then be a fourth plant that receives no water? And the answer here is no. This specifically relates to any of you teaching FET for life sciences, and in grade 8 when you do photosynthesis experiments, sometimes learners struggle with identifying the control when it comes to plants, because it feels like we should be removing the water, we should be removing the sunlight, and why is that not the control? So the answer here is no. A fourth plant that receives no water would not be a good control. Why? Because before you attempt any research, you would have had to have read about whatever it is you're investigating. And a good scientist would know that the basic needs of a plant is water and sunlight. So actually, what you're investigating in this setup is not the water itself. You're actually using the water and comparing it to the other two solutions, because water is the baseline measurement. That is what a plant would normally naturally require to grow. But what you're investigating is whether orange juice or soda would be a better growth stimulant than the water. So that's why the water setup in this instance acts as the control. So a control setup is where you remove the independent variable, yes, but it can also sometimes just be the setup where the natural or normal state occurs. Nothing out of the ordinary happens. So if you think of photosynthesis experiments, if we look at the example of whether a plant requires sunlight to grow or to photosynthesize, the plant that does receive the sunlight in that experiment is actually the control, because the control receives the normal natural condition, the sunlight. What you're comparing it to and what you're actually investigating is what would happen if I remove the sunlight. So the plant in the cupboard or in the dark cupboard is the experiment. That is what you're investigating. The one that receives the sunlight and is going to photosynthesize is your control setup. And then the last one here, we see the results being provided. We see the soda can plant grew 5 centimeters in 1 week. The one that had orange juice grew 7 centimeters, and the one with water grew 12 centimeters. So it asks you to write a conclusion from this investigation. And once again, we're not just going to quote the results because maybe I'm completely deaf and I don't know that 12 centimeters is more than 7 centimeters. I need you to make it clear to me. So what we see is that water caused the most plant growth. We're referring back to the aim, the type of liquid that will cause the most plant growth, that is water. You could also just have said water caused a 12 centimeter increase in height in 1 week. Therefore, water caused the most plant growth. So if learners are struggling with writing a conclusion, they start by just quoting the results. Tell them that if they don't have a therefore in that sentence, they're not making sense of their results. So it's a nice way to get to, okay, so what does this actually mean? Therefore, what I see is water caused the greatest plant growth. Okay. And then we've included one last example that is completely new, where we're going to take all of this together that you can work through with your learners in class. So if we look at this investigation, we have been supplied with the question, what concentration of weed killer will kill the greatest percentage of weeds? You ask learners to first tell you what is happening here. We can see a field A that receives a 15% solution of weed killer. We can see a field B that receives a 30% solution of weed killer and a field C that receives no weed killer. Then on the next slide, we can see results after application. 50% of weeds were killed in field A, 100% of the weeds were killed in field B, and no weeds were killed in field C. Now we're going to ask the questions that we can go through all the different steps. So firstly, what is the aim of this investigation? And we take the question that we're provided and convert that into an aim to determine what concentration of weed killer will kill the greatest percentage of weeds. What is a suitable hypothesis for this investigation? Remember, it has to contain both variables, it must state a relationship, it must be a testable statement. A higher concentration of weed killer will kill more weeds, a lower concentration of weed killer will kill more weeds. The concentration of weed killer will affect the number of weeds or percentage of weeds killed. So many versions of the same thing. Then we can test variables. What is the independent variable? I make it so I determine it. It is the first thing that happens. It is the concentration of the weed killer that is added. The 15% solution, the 30% solution, or none. What is the dependent variable? That is what we measure, namely the percentage of weeds that were killed. Which field is the control setup? Remember, this is where the independent variable is removed or nothing out of the ordinary happens. So it is field C where we have not applied any weed killer. How can the reliability of this investigation be increased? Answers here would be to repeat this investigation or to raise the sample size. So you would use more versions of field A. So maybe 10 field A's, 10 field B's, 10 field C's, and you would calculate averages from those. How can the validity be ensured? When that is asked, you focus on what needs to be kept the same. So we need to use the same type of weed killer. We need to apply it over the same time frame. We need to use the same type of soil, or it needs to be applied in the same area, the same volume of weed killer, the same type of weeds need to be investigated, etc., etc. So with this activity, you can kind of summarize the most important concepts that you've done, the key principles, you gradually increase in complexity in the questions, and you act as facilitator in this activity in class. And that's the presentation that you will receive as a resource when you fill in that feedback form. So to accompany this slideshow resource, you will also receive a summary of the scientific method as it has been laid out in the slides. It is this document that's part of the resources that we will be providing. You can hand this out to learners as notes to paste into their books because it summarizes the whole process. And again, these resources will be made available in both English and Afrikaans. Just stick around for a little while to get that feedback form to provide us with your email address so that we can send that link to you. Another useful resource that is part of this packet is how to read and interpret a scientific investigation, and we have formulated one specifically geared for natural sciences in the senior phase. We have also created a similar one for FET, which is still available on our teacher community page, and we'll share the link to that soon. I'm going to go through some of those resources as well. So the idea to this thing is that it gives the typical layout of a scientific investigation, and it highlights where learners would find certain important things, because in these typical layouts, a lot of information is provided. Very often an aim is given, but learners don't know where to find it. If you can locate the aim, you can locate the two variables in the aim. You can find in the method things that were given, like the size of the sample. Constant variables are often specified, and what is provided in the results, and then some general tips and tricks. So this can really help learners to better interpret and understand questions like this because often the answers are in the text, they just don't know where to look for them. So TAS, which is our acronym for the answer series, if you are wondering, TAS offers comprehensive 3-in-1 class texts and study guides for both grade 8 and 9 in English and Afrikaans. And when we say 3-in-1, it means there are notes, questions, and answers. And in the front of each of these books, we have a thorough skills section where all the concepts for the scientific method, as well as graphs and tables, etc., also appear. There's a whole section on scientific terminology that highlights the important terms, and then we elaborate on planning steps, validity, reliability, etc. We've incorporated a worked example of a typical scientific investigation with exam-type questions and memoranda with teacher talk boxes. So we're telling you why particular marks are being given or what to look for. And when we compiled these worked examples for all our different grades 8 to 12, we looked at NSC trends and we adapted those for the particular level because we know where we need to get to. We also have a detailed section on the drawing of graphs and tables, which is something that obviously was not discussed today, but you need to do that with your learners as well. That would be a whole lesson and more in and of itself. In terms of other forms of support we provide, you may or may not be aware of, is the teacher community on WhatsApp. We have a teacher community for a number of subjects in which natural sciences is one. I'm sure many of you attending here today heard about the webinar through that WhatsApp group. These groups aim to provide support, resources, a platform for interaction and notifications of other TAS projects like this webinar or new releases. They're open to all teachers and teaching officials, and the link to join this will once again be posted in the chat if Gretel or Adriette could do that for us. Again, you can take that link and store it for later so that you can apply to be added to this WhatsApp group. The WhatsApp groups are focused on their specific subject content, and it's not just us at TAS that post and interact there, but it's a community of teachers across South Africa that uses this platform to provide each other with help, sharing resources, asking questions, etc. And if you have any issues accessing the group, you can send me an email. My email address will be shown shortly. Then just two things I wanted to highlight in terms of our teacher support is the ATP lesson planners and trackers that we've compiled for, again, some of our subjects, including natural sciences. This is more than just your standard ATP. It's compiled using a multitude of resources, the DBE ATPs, TAS study guides, resources from our communities, as well as other online resources. So it really is a one-stop teaching solution. On it, you're going to find typical ATP content like what week and date particular topics need to be taught, as well as what percentage they weigh in an exam. We've taken our TAS study guides, we've divided the pages in for you as well as the exercises. So if you are using our study guides, you will get the most out of this document. But if you aren't using our study guides, this is still a plethora of information for you to make use of, because all of these are links to documents or online sources. We've done the thinking for you, and you can track your progress. So it's all of your planning in one place. You can download this document on our community page. So I'm going to ask Gretel and Adriette to please post a link to our teacher community page on the TAS website, and it will be available as the second thing from the top. The webinar currently is at the top, and this will be just below it. And we've done it for grade 8 to grade 12. And then lastly, you're on our YouTube channel today. So we are in the process of creating videos for the grade 8 content. We've been doing this over the past 2 years. We've done, hopefully by the end of this term, the first topic for each term will be available in both English and Afrikaans. And I hope you find these videos very useful because they are visually appealing. Where practical investigations are involved, like in photosynthesis and the atoms or the chemistry modules, we've tried our best to include practicals in these videos and show you ways of doing them with equipment, with minimal equipment. And each of these videos series will also have a worksheet accompanying them that you can download again from our community page or in the video description on YouTube itself. And this serves to prepare learners for exams by showing them a range of questions, but also making sure that they cover the important content in each topic. We aim to expand our video series. We get a lot of requests for this. We aim to expand it as we get time. It is slow going, I know, but it's as we're doing it in between all the other projects that we have going on as well. Right, so that brings us to the end of our session together. Gretel, you are welcome to share that Google feedback form in the chat. Just some closing words by Claude Levi-Strauss, that a scientist is not a person who gives the right answers, but one who asks the right questions. I'm not an expert. We all stand to learn something new each day. And as teachers, we constantly have to self-reflect. Like I said, none of us are perfect. We all stand to improve. So we have to continuously critically evaluate our own understanding and teaching styles by asking the right questions. And I hope you approach this webinar today with a spirit of curiosity, just even if it was to see what a live event looks like. And I hope you see the value of cultivating inquiring minds in ourselves as well as in our learners. So this is just the closing slide with all the ways in which you can contact us. My email address is on there as well. And I'm just going to give some time to see if my team has highlighted any questions for me in the chat, if there's anything that I need to address. Bonnie says no. So if you have any poignant questions that you feel I need to address, you are welcome to share them in the chat. Otherwise, I'm going to say thank you so much for joining us. I really hope you found this presentation useful and that you're excited to use it in class. And if you do, please send me a message to say how it's going. If you find errors on it, please let us know too. We are all human beings. We all make mistakes. So we always appreciate your feedback. Join our WhatsApp group. Stay up to date with what's going on at TAS. There are exciting things brewing for the senior phase. And yeah, we hope to see you soon for another webinar.